Welcome to lecture 7. Today we'll talk about CNNs, or convolutional neural networks. Before we get into the content, I'm guessing you should have received the announcement from Canvas that I pushed the project 1 deadline because we got delayed on the autograder setup. I saw people already submitted and checked out their submissions and looked at errors, trying to resolve. So I think getting familiar with autograder can take some time. So that's why I gave like 2 days. So and project 2 will also be released on Thursday. But if you want to get started earlier, send me an email. I'll send you the files and you can get started, but officially it will be released on Thursday. Okay. What else? I think that's it from the project side. If you have any issues on autograder, let me know. You can also post it on EdStem. You might have already seen people posting it on EdStem and getting answers from there. Yes, Miles? I think I'm going to stick to the deadline on the calendar for project 2. I think getting familiar with autograder is the reason I wanted to like push this. And of course, like if you're done with project 1, you got the perfect score and you want to do project 2, send me an email. I'll send you the project 2 files. The reason we are not releasing it is that there is solution for the project 1 in the project 2 stencil. So we don't want that to be like open. So that's why I think even Michigan folks are mindful about that. They kind of like don't have the project files publicly available. But I guess like most importantly, it's about learning. So I'm guessing the projects are helpful so far. Okay, so it was quiz today, and there'll be a quiz on Thursday. Yeah. Okay, some recap from previous lectures. So we talked about oh, sorry, question.
I just had a quick suggestion. I'm not sure if you up for anyone else, but do you think it would be worth it, like just 1 minute go over the quiz?
I can do it after the class because we don't want to have it on the recording of the lecture.
Oh, sure.
But if you want to talk about it after the class, yeah, I'm happy to answer it. Yeah. Okay. So in the previous lecture, we talked about back propagation, and we saw that autograd functionality only uses a data structure called computational graphs, and that makes it easier and more flexible for you to compute gradients. It has 2 major blocks. One is the forward pass, and the other one is the backward pass. We also saw like locally with respect to a particular neuron or a node or operational node, how to compute the downstream gradients, which we care about, by using the upstream gradients and the local gradients. Yeah. And we also like in the previous lectures, we also saw like how we progressed from linear classifiers to fully connected neural network. And we saw like the similarities between them and how an activation function could help get the non-linearity that you care about into the fully connected neural networks. And so far with linear classifiers and also fully connected neural networks, we always kind of squish the entire input image into a vector. And then we talked about how to classify using a stack of linear functions or a stack of linear functions followed by activation functions. But we care about images, right? So there is information in terms of how spatially each pixel is related to the other. So we kind of losing them so far. So today we'll talk about a particular operation that will actually retain this spatial information, so we can perform much better image classification and also like proceeding tasks like object detection, pose estimation, and so forth. Okay, So yeah, today we'll talk about computational node called convolution. So the components of fully connected neural networks are basically the structure of the network itself and what activation function you're using. And we saw ReLU and we discussed about it at length, how it does the feature transformation and kind of makes regions that are not separable to something that's separable in the higher dimension space. And today we'll add 3 more components. So we'll talk about convolution layers and pooling layers. And I will introduce the normalization, but I'll go in detail in the next lecture on the normalization. Okay, so let's start off with convolution layers. And before we do that, let's do a recap on fully connected networks. So given an input, again, we are squishing the input image into a vector. And then that goes into this linear operation. Let's say there's a ReLU function here as well, but mainly the linear operation, right? So what I want you to understand is, so what is happening here is basically an inner product between your input vector and a row of your W matrix, right? And that gives you that particular one value of the output. And the W matrix is, in this particular case, 10 cross 3072, which means it's classifying 10 classes, or the task is to classify 10 classes. Task is to classify the input into 10 classes. Now, imagine the same thing happening with a spatial structure. So for instance, let's say the input is 3 cross 32 cross 32, an image which has 3 channels, with 32 as the width and 32 as the height. And imagine a filter, or in other words, let's say a template or the row vector that you saw in your W matrix to be a filter of 3 cross 5 cross 5. Now, instead of looking at the entire image, we are talking about, can we do an inner product at a particular location of the image or a particular spatial location in the image? So again, like the comparison between the earlier approach and here is, earlier we were like taking the entire input image and doing the inner product. Here, we have a filter, which is often like small in size, and we want to do an inner product on a sub-region of your entire image. Yeah. And the thing to note is the filters always extend to the full depth of your input, whichever stage it may be in your neural network. And this is very important because it helps you understand other pieces of code that you'll see online. Yeah, so the filters always extend to the full depth of the input. Now, if you do, let's say, an inner product, right, it will give you one particular number at that particular region of the input. Right, you're basically like trying to match up and see how well does it match with the filter that you have, right? That's what's happening. And if you think about it, the dot product here is basically happening on 3 different channels as well, right? So as the text says here, what is the dimensions in which you are doing the dot product? It's basically 3 cross 5 cross 5. And of course, there is a bias term here. So just to add that information here as well. Okay, so now if let's say you do this on all possible locations in the input image, right, you would end up getting an activation map of this sort for every location that you put the filter in the input image or in the input matrix or whatever that is, right? So we call that sliding over your image, and that gives you this particular activation map. As you can note, the activation map has 1 cross 28 cross 28, where 1 is basically the one value that you are getting for every convolution operation, and 28 cross 28 because you are starting off from 1 by 1 location and not 0 by 0 location. So it's shrinking. We'll see that in later slides, but I just wanted to highlight that dimensions is changing for this at this particular case. Okay, so now again, coming back to the fully connected neural network or the linear classifiers, we are talking about a template, right? So it was a row vector in W. Here we are talking about as a filter. So you can have many filters or many templates that kind of tries to figure out if there is a match in the input image. So let's say you have another filter, in this particular case, green filter, and you do the same operation, do the sliding window, and you'll get another activation map of the same dimension, 1 cross 28 cross 28. So now if you add it to this, it'll be 2 different activation maps. Yeah, so far with me. So a convolutional layer is basically a stack of these filters, and you are getting activation maps for each of these filters. So if, for instance, if the number of filters are 6 in this particular case, you'll have 6 activation maps as the output. Yeah. Again, to remember, each filter, the first dimension was same as the input. So 3 in this particular case. And we also have to think about bias term, right? So once the convolution is done, you are adding a value for every filter. Because there are 6 filters here, you have a 6-dimensional vector. Or it's like 6 cross 1, yeah. Okay, so the other way to look at it is this. Instead of looking at it as 6 different activation maps as your output, you can imagine that to be a 28 cross 28 grid, where each grid or each cell has a 6-dimensional vector. A different interpretation of the same output, right? Earlier, I was calling it as 6 activation maps. Now I'm saying there's a grid of size 28 cross 28, where each cell has 6 values. Yeah. Now, imagine doing SGD or like batch a stochastic gradient descent on a particular mini batch. You're always talking about a batch of images, right? So if you include that particular notion here, a convolution layer would take in a batch of images, perform the convolution with how many ever filters you have, and give out a batch of outputs in this scenario. Yeah. So let us put some notions in there. So if n is your number of images in your batch, let's say C in is your depth of the input image or the channels in your input image, and h is being the height and w being the width. And so as I mentioned earlier, the C out here corresponds to how many filters you have in your convolution layer, which means it also determines what is the output size of your like the entire activation maps that you're getting. C in, so this is actually for every filter. C in corresponds to the size of your input or the number of depths in your input. And KH, KW is the width and height of your filter. And the output now you're getting is again same as the batch should be, a batch number should be same as what you had in input, followed by C out, which is determined by number of filters, followed by H hat or W hat. So that kind of determines like what is the width and height of your activation map, or in this case, the output. Yeah. Okay, so we talked about one convolution layer. Let's talk about stacking convolutions. So here is a question. So there is an input here, n cross 3 cross 32 cross 32. So n being the batch number, number of images in the batch, and 3 being the depth of your input. So with the convolution here, let's say 6 cross 3 cross 5 cross 5, and bias being a vector of 6 dimensions, what is the output that you can expect? Somebody else? Nobody? For now, right? Yeah, go on, go on.
Is it 6 by 20 by 28?
6 being the output, like, because you have the number of filters here, right? And then because it is 32 cross 32 with each filter being 5 by 5, you can imagine it's going to shrink, right? So it's 6 cross 28 cross 28. What happens to the next one? Somebody else. I heard somebody saying before.
10 by 10 by 26. 10 cross 26 cross
10 cross 26 cross 26, right? So you can keep stacking convolutions. So now let's think about what is happening if you're just like stacking convolutions. Yes.
The maps and width becomes very small, but it's super long.
Not necessarily super long. We can decide based off of what the convolution layer is going to be. If I keep the number of filters consistent, it's always going to be 6 cross something, 6 cross something cross something, right? So I'm increasing here 6 to 10, 10 to 12. So yeah, whatever you said is correct for this case, but it doesn't have to be a general thing. Yes, Carl.
Are you going for the convolutions are associated with
Exactly. So if you're stacking convolutions, what's happening here is at the end, you'll have a convolution operator. Similar to what we saw earlier before we moved on to fully connected neural networks, we saw there is this concept called deep linear networks. When you are just stacking your linear function without any non-linearity from activation functions. So we have to introduce activation functions here so that they can do the feature transformation that we talked about in the case of fully connected networks. Yeah? Yes.
Can you quickly explain how you got 28 again?
Here. We'll actually go on that in a few slides, like step by step. Yeah. Okay. So again, I think similar to what we saw in fully connected neural networks and linear classifiers, we also want to know like what does these convolutional operations or convolution filters actually learn over the training time. So again, going back to the visualizations that we had from linear classifiers, this is what we saw a linear classifier would be learning if there's one single weight matrix, right? A row of weight matrix, you can operate them or like make them into an image, which would result in a template. And there is an inner product that is happening between this template and the input image to actually classify which of these templates actually make sense for the input image, right? And we also saw that with fully connected neural networks, you'll have a whole pool of templates that will be reused for doing the classification task. So what happens here is we are not looking at a template that would extend to the entire image. We are looking at a filter, right? As opposed to the other two, in CNNs, we are looking at a filter which is not looking at the entire image at the same time. So here is an example from AlexNet. So this is the first layer of the AlexNet. They used 96 filters for so it's an hyperparameter. They fixed their first convolution layer to have 96 filters. And the filter size is 3 cross 11 cross 11. So what you're visualizing is all these 96 filters. This is after training. This is after training with their data. Once it's performing classification tasks, they introspected and saw like what these weight matrices or filters actually look like in the first layer. So for instance, if you pick any of these templates, let's say this particular one here, when you convolve that with your input image, basically you'll get an activation when the input image also, or that particular patch has similar shape or edge feature as this particular template is. So similar to fully connected neural networks, there is reusability of templates that are happening, but it is happening at a different resolution than before. And the thing to note is the earlier networks or the earlier layers in your neural network is somewhat interpretable when you visualize it this way. The later network, the later layers need not be interpretable by us. So here, at least I can say that, okay, there is this particular feature that is being extracted here, right? Whereas, let's say here, you can say that, okay, it is also looking at something that is reddish on the left top corner and greenish on the right top corner. That is something it is learning or the training process. Whereas if you look at the later layers, it might not be as easy to interpret what's happening. Having said that, it's actually an active area of research. So I think I'll post a link to this on the calendar after today's lecture. This is actually a website which we call Distill Pub, and you can play around in the website. I think they have like Java applets kind of thing, where you can play around and see how the later layers look like for a classification problem. And it's very interesting to visualize like what the earlier layers are learning versus what the later layers are learning. So I would definitely encourage you to check it out. Check this website. It's very interesting to see how they do that. Okay, any questions so far? Yes.
So when you first started, you pick like an arbitrary number of filters and do the training process?
It's a hyperparameter. So of course, like over the course in the next few lectures, we will tell how historically the neural networks have been constructed and what is the insight they have gained during the process. So we don't have to start from the scratch. We will start from like building upon other people's efforts to say, okay, let's start with this. I think this looks like a reasonable position to start. Okay. So let's take a closer look at the spatial dimensions. That will answer your question. Let's say we have an input with one channel and 7 × 7 as the dimension, and a simple filter 3 × 3. So when you're doing sliding window, you're basically like trying to move it across the input space, 1 pixel after the other, like both on the horizontal direction and the vertical direction, right? So this produces your output. If you look at it, we did 5 steps on the horizontal direction, even though there are like 7 cells in that direction, right? Because like when we started off from 1, 1, instead of 0, 0. So a formal way of looking at this would be like if the input is W × W and the filter is K × K, your output would be W - K + 1. The thing to note is like, we know that this is going to shrink, like over the period of time. If you stack convolution layers, it's going to shrink. The solution to that would be to add padding. So this is called same padding, meaning like we are trying to add padding such that the dimensions do not change after the convolution layer. So I think there are many tricks to add what values to these paddings. So one common way is to just add zeros, or just use mirror in like values, like just take the values that are from the corner. So there are like few other tricks that you can play to do the padding. Okay, so with padding, you can also have like a different padding if you'd like to. Then in general, you can calculate the output size with this particular expression. So it's W - K + 1 + 2 times P. So you might be imagining like, okay, so the P is always like k minus 1 by 2. What happens if it is a floating value? And I think it's more like designer's choice. You can either try to fix everything to be like, for instance, here the input and filter are odd numbers, so it works out for you, or you can round off the P value. So these are like designer's choice. Okay. So there is this notion in CNNs called receptive fields. I think it's very important to kind of understand what these actually means. So formally, it means that it is a region in the input space that a particular feature in your output or in your layer that you're concerned about is affected by. So in this particular case, this particular location or the feature in this location is affected by those 9 values in your input. You can also say informally, like it's a part of the tensor that after a convolution results in a particular feature. So formally, you're talking from the feature point of view. You can also say like, okay, this particular region actually affects a feature after the convolution. Okay, so we saw that this is for an input output, one particular convolution operation. What if you have a series of convolutions? So here we have 3 convolution operations. So input to this one, and this one to output. So what is happening here is like, if you go from, let's say, from this direction, this particular feature depends on these 9 values, where these 9 values have been derived from the earlier input. So if you look at from the other direction, so this feature depends on these 9 values or 3 cross 3 values, whereas this feature depends on all of these, which means we are looking at 5 cross 5. So all these all these values are basically coming from these 5 cross 5 values. So whenever you add a new convolution layer, your receptive field increases by k minus 1, or the dimension of the region. You good? So you want to understand clearly like what happens for one convolution operation, whereas what happens to your entire neural network. And this is very interesting to keep in mind, because like if you're looking at object detection and so forth, if you don't have a good receptive field, if the object is big enough, it might not even be detected by the neural network because it's not looking at that space in your feature map. So you might have already like kind of coming to this problem where if you have bigger image, you need to have so many convolution layers to be able to have the entire image or like cover the space of the entire image in your receptive fields, right? Because we are moving 1 pixel in terms of sliding window. It might be, we might need a lot of convolution layers to actually have a good receptive field. Yeah, does it make sense? You understand the problem here so far? Okay, so one way to solve that would be to downsample your spatial dimension. So one way to do that would be to add what we call stride convolution. So this will be another hyperparameter that you will decide for your filters. So let's say we have input image again 7 cross 7 with filter of 3 cross 3 and a stride of 2. The output here would be 3 cross 3 because you are moving one step after the other. You are actually leaving the next pixel or the next location. That's the stride. You're leaving one and taking the other one. So again, in general, you can say that the output is basically W minus K plus 2P divided by the stride plus 1. So remember the formula here. W minus K plus 2B divided by stride plus 1. Because I wanted to tell like what is the volume of this particular operation here. So you have the input volume, which is 3 cross 32 cross 32. There are 10 filters for which the dimensions are 5 cross 5. One thing that I'm missing there is it also has 3 as a depth with a stride 1 and padding 2. Yes. Right? Did everybody get it? Okay. So what are the number of learnable parameters? So there are hyperparameters, which is something that we are deciding beforehand, but there are learnable parameters. What are the learnable parameters here? 250.
5 cross 5, 10 filters.
It's more than that.
Is there stride and pad also learnable, or?
No. So those are like something that the designer's choice, right? We have fixed that as a hyperparameter. 750, close enough.
Plus the bias.
Yes. So the thing to remember is the filters are the ones that will have the learnable parameters, right? So the filter size is 3 cross 5 cross 5, right? And then you have a bias term or the bias vector for each filter. That's 76. And then you have 10 filters here. So that gives you 760. Yeah. So always when you're looking at something, try to remember what is a hyperparameter here and what is a learnable parameter here. I think that's very important to look into. And especially here, the filters are the ones that are getting changed. The values of the filters are changing over the training time. So those are the learnable parameters. Okay. So what is the number of multiply add operations? So consider multiply and add to be one single operation. How many are there? Anybody who has not answered so far can try. So what are the operations we are talking about? Like multiply add is basically inner product, right? And you want to think about it from the output point of view. Pranav?
28 by 28 by 3 by 10.
28 by 28 by 3 by 10. Why 28? It's 32, right? We have a padding and
Oh, padding, sorry, 32 by 3 by 10.
so it's basically the number of outputs that you have, which is 10 cross 32 cross 32. So those are the number of cells that you have in the output, which is coming from the inner product. And oh, right. Yeah. So inner product of two things. Okay, got it. Yeah. Yeah, so we are looking at multiply and add operations together. Was this the same thing that you said, Pranav, or different?
I don't think it was.
So we are looking at it from the outputs, like how many operations did you actually have to do to get the output values? And here we are computing product between two tensors of the size 3 cross 5 cross 5. Yeah. Good.
They call this like flops in the literature.
Right. Yeah.
However much care flops it takes for a single.
Yeah.
Loading and putting off.
Cool. One other convolution that you'll probably see very often is 1D convolution, or like, sorry, not 1D, like 1 cross 1 convolution. This is very interesting to understand what's happening here. So when I say 1 cross 1, the width and height is 1 cross 1, right? But the depth of the filter will be same as the input tensor. The input tensor is 64 as its depth. So your 1 cross 1 will also have 64 dimensions. Yeah. And if you think about it, this is basically a dot product between a vector of 64 dimensions with every input cell, which has 64 as depth. Can you think about how this relates to fully connected neural networks? Yes.
Like you want, like, say for a segmentation problem, one channel per segment. And this one allows you to reduce the number of channels at the end.
Yes. So the outcome is like that, but I'm trying to. So the question I'm asking is, how does 1 cross 1 convolution that you see in the slide relates to a fully connected neural network?
Or, I mean, the operation is same. If you just flatten this and do, I mean, put many filters, it's like having two layers of network.
There is one distinction though, like each of the inner products are independent of each other.
Right.
Whereas if you do it the way in fully connected neural network, they're all like concatenated into one vector. But here, we are doing, you can imagine doing fully connected neural network operation on every cell with this 1 cross 1 convolution. So they're all happening independently. And the main operation here is to reduce the size of the input image.
Fully connected.
Yeah, pixel-wise, fully connected neural network. You can imagine this to be pixel-wise. They are independent, right? Like the operation that is being happening, let's say here, for this particular cell is independent of this one. Whereas in fully connected neural network, they are like interlinked because you're squishing everything together before you do the operation. Yes.
When you mentioned it's something like this, what you do on upsampling.
So I was talking about downsampling on the spatial dimension, which is H cross W. Here we are doing in a way dimensionality reduction on the feature dimension. Okay. I think there is one other thing I wanted to say. Trying to remember that. Okay, if it comes back, I'll tell you. Okay. Oh yeah, so what is the difference between, let's say, when would you apply 1 cross 1 convolution, or when would you apply fully connected or MLP, fully connected network? I mean, we already spoke about the difference between them, but like I'm asking a different question, like when would you apply that? Or where, yeah, where would you apply that?
This was spatial relation and stuff with the 1 cross 1 convolution was when you are no longer concerned about the spatial relation. Maybe if you want to apply a normal convolution after this.
Yeah, so exactly. So if you don't, if you're trying to reduce the dimension, irrespective of your spatial dimensions, then you would probably go for a fully connected network because you're trying to say, okay, let's convert everything into vector and reduce the dimension. If you want to like retain the spatial dimension in the same way, you would use 1 cross 1 convolution. Yeah. Something to remember, because like in the architecture that we'll see in today's lecture as well as the next lectures, we'll talk about using fully connected neural networks at the later end when we are trying to squish down to the number of classes that we care about. You cannot do that with 1 cross 1. 1 cross 1 only applies when you are trying to reduce the feature vector length. Yeah. Okay, so here is a summary of convolution. So there is input, C in cross H cross W. And these are the hyperparameters, which is designed by the user or chosen by the user. You can also do cross validation to figure out what these hyperparameters are. One is kernel size, number of filters in each convolution layer, the padding you're using, and the stride. The weight matrix here is C out, which is the depth, which is the output you're expecting, or the number of filters. C in is the depth of your input, and KH, KW are the width and height of your filter. And there's a bias vector, obviously. Yeah, cool. And the common settings that people prefer, or you will see quite often, is that the filters are always square. So KH is equal to KW. And people use same padding because the idea of using padding is to retain the same dimensions for your the output of your convolution layer as the same as input. And you'll often see C in and C out to be powers of 2. That is just because CUDA, which is a specialized library for using GPUs, would often prefer these numbers because of the memory limitations or memory resolutions that you can actually handle. And then you will often see 3 cross 3 as your filter, with padding being 1 and stride being 1. Or you'll see 5 cross 5, 1 cross 1. If you remember, in AlexNet, they used 11 cross 11. So yeah. Cool. So the other types of convolution that you will see are like in terms of it's 1D convolution. So it's not 1 cross 1. This is 1D. So you're looking at the input to be one-dimensional input. And this is common, like if you're looking at temporal signal, like speech signal. And I know some of you are interested in RGBD architectures and point cloud architectures, and you'll see 3D convolutions if you're using point cloud data. It's very important to kind of like remember the sequence in which these dimensions are written out, because when you're implementing, when you're coding, that might matter a lot to understand what's happening. Why do we have 1? Because like if it is, we don't need a singleton dimension. But it actually makes sense to think about from these dimensions, especially inputs and weights. Okay, so PyTorch has Conv2D, like, but for your next project, you will implement your own Conv2D. We won't be using the PyTorch version, but you can imagine using different kind of convolution function from PyTorch for your final project when you're implementing other papers and other work. Okay, so we saw convolution layers. The other way to scale down or downsample your spatial dimension would be to use what we call pooling layers. So the hyperparameters that you would choose when you're looking at pooling layer or pooling operation is the kernel size and the stride that you want to take for the kernel, and what kind of pooling function you're going to use. So one commonly used pooling function is max pooling. So in this particular example, let's say we take one single slice of your depth channel, and let's say there are like 4 cross 4 is the dimension of your input. If you choose your hyperparameter, the kernel size to be 2 cross 2 and a stride of 2, which means it's basically you don't have overlapping regions in your when you're sliding your filter. So basically what's happening is you place your kernel on this location, which is red in color. This is max pooling, so you're taking the max value from there. And then you move the 2 side to this location, and then you do the same operation. So what this basically does is it introduces invariance for instance, if there are small changes like in neighboring pixels, you are invariant to that. This operation is invariant because you're looking at max of a filter region. And there are no learnable parameters here because it's a max operation, right? So that is an advantage. You can use max pooling to reduce your spatial dimension without having a learnable parameters. So that's the advantage of using max pooling.
The same effect be, I guess, technically learned by a network with just like a stride size. Would using a larger stride size in order to reduce the size of an image produce a similar result, or is that a different result?
So yeah, so I think there's a lot of trade-offs, right? Like if you're using larger strides, it's good in a way, but you might not be like capturing all the information that you have in the image. So there is a trade-off of using larger strides versus using, if you don't have any, if you just use one stride, what's happening is your computation is increasing. You're blowing up your convolution operation. By increasing the stride, you are reducing the computational cost here, but at the cost of like losing information from your input. So I think that's the trade-off. Okay, so pooling summary, again, the input is C cross H cross W. The hyperparameters are three different ones, like one is the kernel size and you have stride. And pooling function can be like max or a mean pooling that you can do. And you can calculate the output similar to the earlier ones. And there are no learnable parameters here. So the common settings are to use kernel size of 2 cross 2, the stride of 2, or in AlexNet, you might have seen the kernel size being 3 cross 3 with a stride of 2. So it's like hyperparameters. It's a designer choice. I'm sure like they have done their work to figure out that this is the best for their network. So that brings us to the end of pooling layers. And before we go into normalization, which again, I will cover that in the next lecture. Let's look at a well-known neural network and see how their choice of convolution layer, pooling layer, ReLU function looks like. So here is a seminal work from Jan LeCun. If you haven't heard the name, please Google and search, learn about Jan LeCun. He's one of the Turing Award winners. And this is from 1998 for doing document recognition. So the architecture has like kind of like 4 modules. Like one is a convolution followed by ReLU network followed by pooling, and you have multiple modules of the same, followed by using flattening, and then fully connected network followed by ReLU, and like multiple of them, and then followed by fully connected neural network. So let's step through this. And again, this is famously known as LeNet. Okay, so the input here is a character image. It's a binary image. So it's not 3-channeled input image, it's a binary image. So it's 1 channel, 28 cross 28, followed by a convolutional layer with 20 filters, 5 cross 5 as the size of the filter. And that outputs 20 activation maps, if you remember the first slide, followed by 28 cross 28, because we are using padding of 2 and stride of 1. So we are retaining the size of the input image or the input tensor. And this is followed by a ReLU network, which again retains the same dimensions. because you're applying ReLU function for every element in your tensor. Yeah. This is followed by max pooling with kernel size 2 and stride size 2. So you can imagine, like, when you're doing max pooling, you're reducing the dimensions, like spatial dimensions. And when you do like kernel size 2, stride 2, there is no overlapping region, just like what we saw in the figure earlier, right? So if it is 4 cross 4, we are reducing that to 2 cross 2. In this case, it was 28 cross 28, we are reducing that to 14 cross 14. Yeah, with me? Okay. And then a convolution followed by a ReLU operation. Here, they are using 50 filters. And the input size is the same as, sorry, the filter size is the same as the input size. And the dimensions that are being chosen here is 5 cross 5. With the padding of 2 on stride 1, you are retaining the same size as the input. Yeah. Followed by ReLU, again, you're doing ReLU for every element in the tensor. Okay, max pooling, again, kernel size 2, stride size 2. It's being scaled down by a factor of 2. And there is a flattening operation. This is basically converting your entire matrix or tensor into one vector, or one vector tensor. So this is where you lose your spatial information to some extent. And this is followed by a linear, which means fully connected neural network, and followed by a ReLU. The fully connected neural network here is basically doing dimensionality reduction, right? It's so if again remember how we discussed about like 1 cross 1 versus fully connected. Here we don't care about spatial resolution anymore because it's already flattened. So we're just using fully connected neural network to reduce that to 500. Again, a fully connected neural network that reduces 500 to 10, which gives you the number of classes. So they had 10 classes in there. I think the illustration just picked 10 classes here, but like you can imagine that is the number of categories that you care about. Okay, so if you have noticed, as we progressed, the spatial size decreases. But because we are like increasing the channels of your filter, you are trying to like retain the volume to some extent. So earlier it was 20, and then here we used 50, even though we reduced the size using max pool. So that is something that is commonly seen, like when you're going deeper into the network, the number of filters for your convolution layer would increase, while your spatial resolution is getting decreased. Yeah. But for more recent works, I think this is changing. So we'll discuss that in the future lectures. Okay. Any questions so far? How did they figure this out?
These filters they're initialized with just random weights.
Yes. So random weights, and we'll talk about like how well I'll give a brief introduction to normalization that tells like how the choices are made for doing the initialization, and how they are like kind of bounded to certain values over the training as well. Okay, so deep networks are very hard to train, and to kind of have a control over that, more recently we saw a technique called normalization, and more specifically batch normalization. And I will give you like a basic idea here, but we'll discuss in detail in the next lecture. So again, we do not know how this works. It just does, but these are like some intuitions that was given to be able to say that the batch normalization is done for this particular reason. So over the training phase, let's say you are waiting for the output of earlier network. And let's say the values are changing quite a lot. There's a huge shift from the previous time step to the current time step. That kind of like puts your current layer or throws it off. And it's hard to optimize when this kind of behavior is happening over during the training. So what batch normalization does is it takes the output of a particular layer and bounds that between, let's say, zero mean Gaussian, so that the values that you'll get as an input to a layer would always be bounded. And they show that the results are like they show that it is efficient to learn using batch normalization than not using that. We'll go into the details in the next lecture. And in summary, what we saw today was these components for CNN. Again, we saw fully connected networks early on in the previous lectures. And also we talked about activation functions, but we kind of introduced convolution layers and pooling layers in this lecture. We also saw a classical architecture and how they have structured these components to be able to achieve image classification, or in that particular case, document recognition. Okay, so in the next lecture, we'll see CNN architectures. I also wanted to like give a small overview on the final project. I got a few questions during the office hours. I want to like, and I'll clarify over the next lectures. This is me starting to think about, because like the group formation is currently happening, depending on how many number of groups are there, things will change accordingly. Okay, so so again, this is a final project instead of final exam. The objective here is that I want you guys to gain experience, hands-on experience in looking at research papers and see how we can re-implement them, or how to think about re-implement them, or how to understand these papers. And we want to be able to reproduce their results, meaning you will write your own neural network architecture by looking at their schematics and try to see what went into it. So you learn about the nuts and bolts in coming up with a neural network. It's always good to have a base or like somewhat grounded by an existing work. So you know that this works and they have produced the results. So you can try to reproduce the same thing. And while doing that, of course, like we are looking at it from a very broad picture. You'll have other people present their work. You'll have different ideas. You might read multiple papers. You also want to think about how to extend that piece of work with either, let's say, like trying to apply that on a new data set, or maybe adding something to the neural network and see if that improves, or trying to apply that to a particular domain that they have not applied. So I want you to think about these aspects when you're narrowing down your paper for doing the implementation. Ideally, I would encourage to have 3 people in the team, but 2 to 3, I think, could work as well. I wouldn't encourage one person doing a project unless they have some ongoing research and they want to like build on top of it. They have to like, come and talk to me. But yeah, ideally 3 people, but 2 is also fine. 1 probably not, but I can make a special case if they convince me. Okay, so so this is being changed from what I introduced in the first lecture. So these are the tasks for your final project. So I've listed some of them to be graded because you'll be graded for that. There are 2 tasks where you will have to do that to get feedback from your peers. The first thing is project proposal as a document that has to be submitted. So that will be graded and you'll have 3%. And there will be an in-class topic papers presentation. So let's say there's a group of 3 people or 2 people, they're working on, let's say RGBD architecture. As a group, I want them to drive that lecture, meaning one person can focus on related works or what is RGBD, like give an introduction to RGBD data, where it is being useful, and what people have done in the past to use RGBD architecture or use RGBD data for doing some perceptual task. And then introduce what is the architectures that are out there, which means the group will be analyzing other papers in the same space. But then they'll focus on one piece of work that they are going to re-implement and like give technical details about that. Some of these papers have code available, which means one member can actually try to run the code that is available and show a result of what they were able to do it. Again, all the papers might not have code, but like some of them do. It's good to see if you can run it and have some baseline that you can compare with. So yeah, so in class topic paper presentation will be assigned based off of the group's topic and paper interest. And this will happen soon in the next couple of weeks. And once a group figures out what their project is, they have to do around 10 minutes presentation in the class. So we'll have one lecture completely dedicated to basically, you have a slide deck of all your slides, and we'll just like go one by one. And during that presentation, I want them to convince not only me, but also the other groups that they have good amount of work that is distributed among their members. And they do have ideas of replicating or reproducing on top of it. So we will have like voting by the other groups when one group is presenting in the, so we can understand like, is it reasonable to have that project, or do they need to like add more, or is it too ambitious? Should they like cut it down? So we'll have that during the pitch presentation. And after a few weeks, we'll have a checkpoint. Again, it will be in the same format, but now the groups will talk about like, what is the current phase of their work? What is that they proposed? Where are they at? Are they going to like proceed forward? Are they going to like change the plans? So we'll have that during the checkpoint. And I also want to mention that it's always good to have plan A, plan B in your proposal document itself. So let's say you're shooting for something, but you also have a fallback option if things don't go your way. Yeah. And I think that's a good practice to have whenever you're approaching a research project or any project in general, to think about like, what is your plan A and plan B. Okay. Then you'll be graded on how you're reproducing the results. So one thing that I'm planning to do is like, if you're using a GitHub repo, you'll give access to me and also other members, so they can like vote based on, is it completely implementation, pure new implementation, or did they use like some chunks from the existing work? It is okay to use the chunks from existing work as long as you have more thing that you worked on to make it work. Okay, so reproducibility. And I also have a slide. So it also contains the aspect of extending, because not every paper can be extendable. So if the group wants to focus only on reproducing the results, then that is okay. But it would be nice to see what they can extend it to as well. Again, that will be kind of decided by the peers. I think they will give the scoring based off of what they think the group has done. So we'll have final presentation, and I want to do this as video presentation and poster. So imagine you have a poster and you have a laptop, and we'll have like people coming in talking to you, so you can talk about your work and show off your video as well. And final report. Final report is to actually add details that you have not been able to add in your video or the poster. So it's actually in one document. And I also want to emphasize that at the end of the course, I want you guys to come up with like a project that you're proud of, and then you can list that video and the report in your resume. I think it makes a huge impact when somebody is reading your resume and there is a link and they click on it and there is like 3-minute video that showcases, oh, so this person did RGBD architecture on this particular data and it works. I think that gives more signal about the capability of the candidate than like 3 lines in your resume. That's my view. And I want you all to have a project page or like maybe a video that you're like proud to talk about out of the course. So that's why I'm emphasizing on the video presentation more so than the report. But I also have like few pointers on how your videos could be very compelling. So we'll share that towards the end of the class. Okay, so with that, just wanted to highlight. So there is a project pitch on March 14th, and I have updated the calendar. So you should be able to see that on the calendar. And there's a project checkpoint on 11th, which is actually pretty close to the final presentation. But I'm guessing if you have any issues, you should already have resolved that. But it's good to have a checkpoint to say, okay, you have 2 weeks to, or roughly 2 weeks to finish up the stuff. Okay, with that, this is the end of today's lecture. Thank you.